Yeah, moving to unit 3, process dynamics and control, unit 3, that is stability and root locus. So basically you need to define the stability of a system. In this unit you will determine how the system is stable, on what basis the system is stable, how do you determine the roots of the characteristic equation, and what are the different methods available to check whether the system is stable or unstable. First, we need to define stability. That means a system is said to be stable. A system is said to be stable if and only if the output response is bounded for all bounded inputs. That is nothing but, for example, I'll take and sinusoidal input, which is nothing. Sinusoidal means it's a sine curve. Sine curve has a range, means it is bounded within some values, right? So for that sinusoidal input, if your output is also a sinusoidal curve, that means it is also bounded, or it can also be a cos curve, doesn't matter, it is also bounded. So for if the output response is also bounded for all the bounded inputs, then the system is stable. Okay, and if the output response is unbounded for all the bounded inputs, then the system is said to be unstable. That means, for example, if you have an sinusoidal input I am giving to the function, this is the input, and if your response comes to be a step response or an impulse function, then for a step response, if you take it increases to a certain value, then it is constant throughout somewhere and we don't have a certain limit for that, right? So in such cases, or also in sinusoidal curve, it is bounded from 0 to 1, for example. In some cases the output might be continuing. In this case it goes on continuing, it is not bounded, means it doesn't have a particular range, it is not bounded within certain regions, then the system is said to be unstable. That is, if the output response is unbounded for the bounded input, if the input is always within a given range, and if the output comes to be also in some range, not only in this given range, it can be in any range. If it comes in some range that is bounded, then it is stable. If it doesn't have any bounds, no limits, it continues, then the system is said to be unstable. This is what is the definition of stability. Definition point of view, stable and unstable is this. Now on what basis you can say, that is, on what basis you can say, or how can you say that the system is stable or not? So for that you will consider the stability criterion. So for considering the stability criterion, first we will consider an open loop. So for this open loop, you have to write the characteristic equation. Characteristic equation is nothing but the equation which is 1 plus g of s is equal to 0, where g of s is the product of all the transfer functions present in the loop. These are the transfer functions present in the loop. It can be more than 2 also, or it can, here also you can have many, here also you can have many. So this is just an example. That is, g of s will be product of all the transfer functions present in the loop. It can be more also, okay. So characteristic equation is 1 plus g1 g2 h is equal to 0. So this is what is the characteristic equation. Now to know the stability criterion, consider real axis and imaginary axis, plus I, minus I. I hope what is imaginary axis you all know. 1, 2, 3, minus 1, minus 2, minus 3, 1, minus 2, minus 3. Now you have the characteristic equation 1 plus g of s is equal to 0, right? For that characteristic equation, if the roots lie on the left hand side of the imaginary axis, that is the negative side of the real axis, left side of the imaginary axis or on the negative side of the real axis, that means here or here or here or here or here or on this axis also, then the system is said to be stable. If the roots of this characteristic equation lies on the left hand side of the imaginary axis or on the negative side of the real axis, then the system is stable. It can be whether above, below or on the axis, doesn't matter. Left hand side, if it is there, it is stable. If any one of the root of this characteristic equation or more than one of the root of the characteristic equation lies on the right hand side of the characteristic equation or on the positive side of the real axis, then the system is said to be stable. Unstable. If the roots of this characteristic equation, whether a single root or any one root or more than one root also lies, any of the root lies on the right hand side of the imaginary axis or on the positive real axis side, whether it is here or here or here or on the axis also, then the system is said to be unstable. Then if the roots of the characteristic equation lies on the imaginary axis, on this axis, if they lie on this imaginary axis, then the system is said to be in the verge of instability. Or close to instability. So this is what is the stability criterion. So roots, if they lie on the left hand side of the imaginary axis, stable. Right hand side, unstable. On the imaginary axis, verge of instability. Next, where is the duster? Next, the two important concepts of this unit for 10 marks is Routh's array and root locus. These are the two important topics, long answer type questions in the unit 3. So we need to focus on them. First, we will discuss about the Routh stability. Routh stability. So Routh stability basically helps us to determine whether the system is stable or unstable. Okay, for that also we will first consider the characteristic equation 1 plus g of s is equal to 0. I hope you are clear with how to calculate the characteristic equation. If still you have doubt, move to the reverse in the video and just check it. Still if you have doubt, you can call me. Okay. Now, characteristic equation you have found out, and if the main important condition of this Routh stability, or you can say limitation of this Routh stability, is the characteristic equation must be of the form a naught s power n into a1 into s power n minus 1, a2 s power n minus 2, a3 s power n minus 3, and so on. An is equal to 0. It should be in the form of whole number. Okay. So now, to find whether the stable or unstable of the system, you have to construct the routes array. Please listen very carefully. I'll just tell you how to construct it. Further calculation, how do you do? I'll explain when we do the problem so that it will be more easier for you. So first construction we'll see. So first basically this is how you display that routes array table. On the first row of this route array, you will put all the odd terms. First term, third term, fifth term, you'll have one more here. Okay. So that is A0, A2, A4 and so on it goes on. Depends on the equation it is. On second row, you will have all the even terms. Second term, fourth term, sixth term and so on. So A1, A3, A5, so on. And this AN, depending on the position of that, whether it is an odd position or even position, it might be in the first row or on the second row. It depends on the position. Okay. Next are the just constants B1, B2, B3 and so on. C1, C2, C3 and so on. D1 and so on, so on. It continues. Till where it continues and how to calculate those constants, I'll let you know on the problems. Now, for discussing about the stability, we have three theorems which is given by Rao. If all the values in the first column of the route array, if all the values in the first column of the route array are greater than 0, that implies the root of this characteristic equations are negative. That implies the roots of this characteristic equation is negative, then the system is stable. If the values of the first column of the route array are positive, which states that the characteristic equation roots are negative, then the system is said to be stable. Or in simple, if these all values of the first column are positive, then the system is stable. In simple, you remember that this column should have all positive values, then the system is stable. If any of these values goes negative or less than 0, not less than 0 means not point, less than 0 automatically it goes to negative value. If it goes to negative value, then it is unstable. Or indirectly, if the column values, any of the value in the first column of the route array is less than 0, which states that the root of these characteristic equation are positive, then the system is unstable. In simple, you will just remember when you are doing problems, in this column, that is the first column, is all the roots are positive, stable. If any one is negative, also it becomes unstable. And now if the system follows, or if the characteristic equation follows the condition Cs square plus D is equal to 0, if the system follows the condition Cs square plus D is equal to 0, where C is nothing but the coefficient of S square in the characteristic equation and D is the constant value. If it follows this condition, then the system is said to be in the verge of instability. Verge of instability. Clear? Very important concept. If you understand this, you can do the problems very easily. Route stability, characteristic equation should be of the form A0 s power n, A1 s power n minus 1 and so on. Now, route array construction, first row, all the values will be the odd terms, first term, third term, fifth term coefficients. Second row will be all the even terms, A1, A3, A5 and so on. Next are the constant B1, B2, C1, C2 and so on until where it continues, and how to calculate we will discuss in the problems. Now, to determine stabilities, you have three theorems. You might ask me in the question sometimes, state the theorems of route stability. Don't get confused there. It is nothing but if the first column of the route array has all positive values, it is stable. If any of these values of the first column of the route array goes negative, it becomes unstable. If the system follows the condition c square plus d is equal to 0, where c is the coefficient of s square and d is the constant value from the characteristic equation, then the system is said to be on the verge of instability. Clear?